Let's understand ocean currents, the Earth's circulatory system. Think of this as a three-part lesson. Concepts first, then the forces that drive currents, and finally, the impacts that UPSC actually tests. If you get these three right, ocean currents stop being a map memory topic and become a logic topic. To begin, picture a river inside the ocean. That is exactly what an ocean current is. A continuous directed movement of ocean water. Now notice the split on the slide. Surface currents are wind-driven and they are only about 10%. Deep currents are density-driven and they form about 90%. This is a common mistake in prep. Most people over-focus on surface arrows on maps, but the real volume is in the deep circulation. Now separate the ocean into two working layers. The surface layer, roughly 0 to 400 meters, behaves like sprinters. Fast response, driven by wind and shaped by the Coriolis effect. Then you hit a boundary called the thermocline. It is a temperature barrier, so mixing across it becomes difficult. Below that is the deep ocean. These are marathon runners, slow, persistent, and driven by density, meaning thermohaline forces. Now we ask the engine question. What actually starts the flow? The slide gives you a clean sequence. First, insolation. The equator is heated, water expands, and sea level rises. Second, gravity. That slightly raised water wants to move down the slope and flow begins. Third, wind. Wind does not start the current. It transfers momentum and sustains movement. The line in the box is worth remembering exactly. Gravity and insolation initiate the flow. Wind sustains it. This is where many aspirants invert the cause. Once flow exists, it needs steering. That steering wheel is Coriolis, and the large circular systems it creates are called gyres. In the northern hemisphere, the dominant rotation is clockwise, meaning a rightward deflection. In the southern hemisphere, it becomes counterclockwise. And notice the label in the North Atlantic. Sargasso Sea is shown as a stagnant zone. UPSC sometimes tests such named ocean regions as indirect current indicators. Now shift from wind to density, the deep driver. High-density water is created by cold temperature and high salinity. Low-density water is created by warm temperature and low salinity. So what happens at the poles? Dense water sinks. And where does water rise? In upwelling zones. This creates a vertical circulation that connects surface to deep. That one line is the bridge between surface geography and deep thermohaline circulation. Now, how do you classify a current quickly in prelims? Use the direction rule. A warm current moves from equator to pole. A cold current moves from pole to equator. And there's a hack which you can use to avoid guessing. Do not guess the temperature. Look at the origin. From pole means cold. From equator means warm. Now we apply this to a real basin, the Atlantic Circuit. Track the warm Gulf Stream starting from the Gulf of Mexico and moving northeast. Then notice the cold Labrador current coming down from the north. Where they meet, the slide marks a fog zone. This is a classic map-based application. Warm meets cold, condensation, fog, and often fog banks. On the eastern side, the Canary current is shown flowing southward along northwest Africa, a cold current. In the South Atlantic, the Brazil current is a warm current along the east coast of South America, while the Benguela current is a cold current along southwest Africa. Now move to the Pacific and Indian circuits. In the Pacific, focus on two names. Kuroshio current is shown as the Gulf Stream of the Pacific, meaning it is a warm western boundary current that significantly affects nearby climates, here, Japan. On the other side, the Peru or Humboldt Current is shown as critical for fisheries. That is your clue that it is a cold current linked to upwelling. In the Indian Ocean, the key phrase is monsoon reversal. Currents here are not as fixed as the Atlantic gyres because seasonal winds reverse the surface flow. And near southern Africa, the Agulhas current is marked. This is a warm current and often appears in UPSC map questions as a western boundary current of the Indian Ocean. Now we connect currents to deserts and asks a very exam type question. Why deserts are commonly found on western coasts? Here, the mechanism is explained in 4 steps. 1. Cold current on the west coast. 2. It chills the air above. 3. That reduces evaporation and suppresses rainfall. 4. The result is desert. And the UPSC favorite line at the bottom is the real framing. Cold currents create aridity because offshore winds and cold water suppress precipitation. That is how you write it in mains, not as a one-line fact. Now the food web angle. Upwelling. The slide shows offshore wind pushing surface water away from the coast. Then deeper water rises along the continental shelf. This is upwelling. That deep water is nutrient-rich, so plankton blooms. Plankton increases, fish abound. The example given is the Peru coast, and it matches what you saw earlier with the Humboldt current. Now add one more driver that students ignore: coastline configuration. It includes geography as a divider. The South Equatorial Current hits the Brazilian landmass at a point marked as the point of the wedge. Because of the coastline shape, the flow splits. One branch goes north and becomes the Caribbean Current. The other goes south and becomes the Brazil Current. So the takeaway is direct. Coastline shape dictates current direction. Continental margins can physically split major currents. Now bring in a contemporary application, the changing Arctic, called Atlantification. The diagram shows sea ice on top, a layer of fresh cold water, and below that, warm salty Atlantic water encroaching into the Arctic. The key phrase is heat from below. Warm Atlantic water is melting ice from the bottom up. This is the kind of concept UPSC links to climate change, ocean circulation, and polar changes in both prelims and mains. Now we close with the master cheat sheet, because this is what revision should look like. Gulf Stream, Atlantic, warm, and it warms Northwest Europe. Labrador, Atlantic, cold, and it creates fog banks when it meets the Gulf Stream. Peru or Humboldt, Pacific, cold, and it links to the Atacama Desert and fisheries. Kuroshio, Pacific, warm, and it shapes Japan's climate. Benguela, Atlantic, cold, and it links to the Namib Desert. Canary, Atlantic, cold, and it links to North African aridity. Treat this table as a last-minute prelims checklist. Your map questions become predictable and you are exam ready.